Introduce now the index notation, which can be used for vectors, matrices, and other high-ranked tensors for algebraic manipulation. It will prove to be much more powerful than the standard vector notation. To clarify this, we'll translate all well-known vector and matrix manipulations to index notation. Consider the transformation U is equal to A V, where A is a matrix. In matrix form, this is the equation. And according to the rules of matrix multiplication, what you're doing is that you're multiplying the first row by the column to get the first value, U1. The same for the second, the same for the n. Notice that this is a sum. You have repeated indices here, 1 and 1, 2 and 2, n and n. So for every row, you can write this as a sum over a repeated index j. Ai j times vj for u1, for u2, for un. So you can write this even more compactly, saying that you have here an index that is going from 1 to 2 to n as the index I. And then the summation here is repeating this index I. And then you have this following this index I and repeating the index j. So this formula has the essence of matrix multiplication. The index j is called the dummy index, and I is a running index. The names of these indices, in this case I and j, are completely arbitrary. They could equally well have been called alpha and beta, leading to this equation, and these two equations are equivalent. So the following statements are equivalent. V equal to y, a vector v equal to a vector y. You can write this with the arrow. You can write this in component form, giving a subscript I or a subscript of any choice. This means that the components of each of these vectors is equal, be that a component that you call I or a component that you call alpha. And for matrix multiplications, you can say V is equal to A times Y, where A is a matrix. You can write that again in vector form, or you can write that in summation form. Vi is equal to Aij times Yj, so the j here is repeated, leaving component I, or then you can give any name to the components. The index notation is also applicable to other manipulations, for instance, the inner product. Say that you have two vectors v and w, and you can find the inner product as v dot w. Here you have then the summation component-wise of the two vectors. So you can write this as a summation over a repeated index k from 1 to n.